Hi, this is Group 20. I'm Aditya and my teammate is Anul. So, our project is a study on predicting social unrest using GDELT data. So, coming to the introduction, the GDELT data is a 250 GB data set which contains news data that's global. And this data has been collected over the last around 40 to 50 years. So, it's a very large data. So, our aim is to predict a future global unrest based on this news data. And our data includes this GDELT data and the ACLED data, which is a non-conflict data set. Now, this is our proposed solution. So first, we have the GDELT data and the ACLED data, and we combine it into a final data set that we use. We have built 8 different models that we train on this combined data set, and we have also tested our metrics based on the same data. We use this learn model to predict future unrest globally, given a news article as an input. So these values on the right show the unrest events we are trying to predict. So it's a Y event map and there are 25 such events. So some of them include, peaceful protests with intervention, and our models aim to predict the probabilities of each of these Ys happening. Coming to the motivation behind predicting future social unrest. So the first one is it aids humanitarian organizations like the UN, and it helps them, send emergency response teams to locations that could have social unrest in the future. Of course, the same point holds when it comes to mitigating unrest events, and it helps emergency services like the police and ambulances to go to locations that could have future unrest. It helps the government and bureaucrats with informed policy making that is data driven, and it also helps them allocate resources accordingly. Now, my teammate will continue with the challenges we faced.
Hey, this is Anul. I will be taking you through the challenges that we faced in this project. I'll address the technical and financial limitations that we faced. We worked with GDLT data, which has multiple kinds of data available in it, and we chose GDLT 1.0, which has the raw CSV files, raw data of close to 4 decades available in it. This data set was of approximately of size 250 GB, and uh, this huge data set, this huge size of data set, coupled with different machine learning models such as GNNs, posed a computational restriction on us, wherein we needed extensive resources in our computers, which was just not available for us. Apart from that, we used large language models, and there was also a financial restriction on that endpoint, wherein we need to pay for each API calls that we made. Uh, uh, Talking in terms of research limitations, there's a lack of baselines available for evaluation purposes. Most of the papers addressing these topics only talk about metrics in terms of quality, and they don't quantitatively assess their metrics. Uh, this this comes due to the inherent complexity of unrest event prediction. The state of the art systems like Ember basically have around 70 percentage of false positive rates. So the problem itself is inherently complex, and we faced we faced issues finding relevant research in the field. Additionally, we had planned on working with causal inference, but causal inference is an up and coming field wherein research is currently being done with no real packages available for easy deployment, and thus we had to find a way to work around that. Moving on to the novelty of our idea. Our idea has been um, worked on before, but and I believe that this is the first time that an ensemble training model has been proposed to address this problem. We've proposed graph neural networks and large language model networks as a part of our ensemble training model. Um, Along with that, we've also combined ACLE data for prediction of the unrest events. We have also addressed different transfer learning approaches such as XGBoost and TabNet. Next, I'll address the results of our project. We found that traditional models have a good balance between the accuracy that they predict with as compared to the computational resources at the time that it takes. Newer models such as LLMs and GNNs do provide higher accuracies, but it comes at the cost of higher computational resources and time. More details and metrics have been provided in P4 submission document. And now we'll go through the code and walk through our demo of the UI. What this is our UI wireframe, and what our wireframe basically showcases is that we select all different kinds of inputs for our news event and select a model that we want, pass it along with the data, and we can get predictions for the inputs that we give it. So I'll give an example of neural networks. While it is fetching a prediction, let me take you through each of these input fields over here. Actor 1 and Actor 2 basically showcases what the subject and the object of the news is. Event code is a cameo coding standard for different news events. Action geo is basically the location of where the action has taken place. Importance is how many times the news article has been mentioned or linked to. Scale mode basically showcases what it's a combination of how the news sounds like, the tone of the news, along with the Goldstein scale of the news. And similarly, Actor 1 geo and Actor 2 geo are just the locations where the Actor 1 and the Actor 2 are physically located in. As we can see, the neural network has given out predictions for 25 different columns. These 25 different columns stand for 25 event types that are there in our event database. And similarly, if we take a look at LLM, we can have a custom prompt for our LLM model. But for now, we'll just run this and we'll see what kind of output it gives. So yeah, so it gives out an output of F, which is again mapped to 0 to 25 of our event of our event database. Similarly, we can also get maybe tabnet. We'll check, and tabnet should generate predictions for, yeah, for all the 25 events. This is, yeah. ATDS. Okay, now I'll be taking you through the visualizations that we use to understand our data set. Um, so we have visualized different column distributions. We have a scatter plot, both for our GDLT data as well as our ACLED data. We derived some interesting insights from it. One of them being that our data is indeed imbalanced in terms of classes. Some classes occur way more than the other ones. For example, peaceful protests occur at a much more higher frequency than maybe violent protests. Similarly, if we look at our scatter plot, we see that the number of mentions and articles and the sources are very clearly correlated. Um, an interesting observation is that the highest correlation for news is between the Actor 1 and the action, followed by Actor 2 and the action, and lastly, correlation between Actor 1 and Actor 2, which indicates that Actor 1 and Actor 2 are different in most cases. Um, Now, I think I will hand it over to my colleague Aditya, and he will take you through all the models.
I will now take you through the code for our entire project. So to start with, we have our base codes notebook. The first thing we do is pre-process our data. So here we have set the column names that we need from the data set, and then we drop a bunch of columns that we do not need. And then we calculate importance as a score of number of mentions plus number of sources plus number of articles and average that out. So this gives us an insight into how important a news article is. So that would be one entry in the data set. Then what we need to do is, we since we have around 30,000 news articles for each date, we just pick the top 100 news articles based on the importance we have previously calculated. So this is because just to reduce our data size, and it stands to show that only the most important news articles really affect a country's social unrest. And this is our ACLED data set, which gives us data about the events we're trying to predict. So here we have a Y event map. So this is from the ACLED data set. So as my teammate mentioned earlier, you would have noticed our UI predicting these values as outputs. So maybe between A to Y or Y0 to Y24 or 25 different columns. So each column stands for a different kind of social unrest event. So for example, A stands for government regains territory, and E stands for protest with intervention, F stands for peaceful protest. So this is what most of our models are trying to predict. Now, going back to the code, so then we need to map our ACLD dataset to our original GDELT news data. So that's what we do for the pre-processing part. And here we have our event indexes and reverse event indexes to map the countries, map the events. Yeah, then we also need to perform one-hot encoding because most of our columns are categorical, like country codes. So we need a model to understand that this data is not ordinal. Yeah, then we do the train test split. So now, because of time constraints, I won't run every model, but I can show you this is our base neural network. I can show this training on a small bit of data. And what we've noticed is that this model does not give us very high accuracy. It gives us 30%. But comparing this to our baseline, since social unrest prediction is a complex problem, it's still pretty decent results. And when you print predictions, this is what we get. So what this is doing is for each row in our test data, it gives a probability between it gives a probability to of each entry in the row being a part of one of these events. So the first column stands for A, the and so on. Now, similarly, we've built multiple such models to compare the accuracy on different metrics. So this is our random forest model, and here we're getting a far better accuracy of around 70%. So I won't be training the model again for time constraints. And this is our predictions for the random forest model. So as you can see, if you look at Y0, which is government regains territory, there's no positive entry that the model has predicted. But coming to something like peaceful protests, you can see there's a lot of, so for our test data, the model predicts that it's possible that there's peaceful protests for that specific news entry. So given that news entry, it's possible that there will be peaceful protests between the actors in the news entry. So that is a random forest model. Now moving on to the KNN model. So here the metrics provided by the KNN model were pretty disappointing. So we're getting an accuracy of close to 50%, but we were expecting more, and we will be working on that in the future. Um, Again, so here these are the predictions made by the KMM model. So we have again around one entry for here and there for each row. For example, in peaceful protest, we have one entry for the sixth row, but it should have been a lot more. Now moving on to an SMM model. So we wanted to use the SMM to understand underlying patterns in our input data. So and what we've learned is that SMM is not able to converge. So that is another thing we'll be working towards in the future. But it's still able to predict one hidden state for each row in the sample. As of now, our understanding is that the hidden state could stand for one of for these classes, since it's predicting up to 21 hidden states for each row, which means it's giving a value between 1 and 25. So it could mean that the hidden HMM is predicting the class itself, but we are not sure about this. Now moving on to a graph visualization. So a graph is a very good way to visualize news data, since we can directly visualize links between different actors, different countries, and the events that link them. So we use Network X just to visualize the graphs. So this is a sample graph. So we've done one graph for each month, for each day in a particular month. So here you can see there are links between different countries and events, and there could be multiple different edges linking these nodes. So we'll come back to the graph neural network soon in more detail. Yeah, then the final models we tried were some transfer learning models. So these models gave us the best results we've got for this data. The first one was a PyTorch model called TabNet Regressor. So after running the TabNet Regressor, these are the predictions we got, and we're getting an accuracy of around 45%. But then when we move on to the XGBoost model, so the XGBoost model was giving us very, very high prediction accuracies of over 90. And what the XGBoost model says is that given that on predictions on the test data, it's predicting a lot of um, peaceful protests and other protests. So as you can see, there are a lot of predictions being made for column Y4 and for column Y5. Now, if you compare that with our event map, Y4 stands for protest with intervention and Y5 stands for peaceful protests. So these are a lot more common than the remaining events that I mentioned here. Now, moving on to the GNN model. So since GNNs are very data heavy and they're difficult to train, so we just trained it on 1 month of data. So what we've done is we have made one graph for each day in that particular month. So I will show you the graphs that we have made. Yeah. So the graphs I showed you earlier was using NetworkX. These graphs are built using the DZL library. So yeah, we've taken Jan 2022 and we've made one graph for each day in Jan 2022. So these graphs show the links between two different countries. So this is a country and this is a country, and it's linked by an edge. The edge holds weights such as the scaled mode. So scale mode is a negative or positive value that shows whether an event is negative or positive, and it also shows the edge also holds the our predicted event. So these this data. Yeah. So now what we're doing is we're combining all these 30 graphs into a data loader to be sent to the GNN, and then we train. So the GNN we're using is we built it using the DZL.NN library. So we're doing a edge predicting GNN, and here also we need to process the data. So some some cyclic edges have to be created between the nodes to make it compatible with the GNN. And as you can see, some nodes also have an inherent cyclic this thing. What this means is that both the actor one and actor two in that news entry had the same, with the same actors. So now we train it on the combined graphs, and then when I give it a test graph without any edges, the GNN should be able to predict the edges along with the weights. So here I'm just visualizing what the GNN has predicted. So as you can see, if it was given a graph with just nodes and no edges, it can predict edges between them. So the green edges stand for higher probabilities. So as you can see, this is 0.78, and here we have probability of 1. And it shows that there is a almost guaranteed chance that an event of type, whatever it's specified here, will happen between these two actors. So there is a map between the numbers here, 26 and 0, to the actual countries they stand for. So yeah, that is what our GNN is doing. Now coming to our final model, this we use the OpenAI GPT's engine, to predict the events. So again, we do the same data pre-processing for the LLM. So what we do is we use the Langchain library to tokenize our data. So yeah, here we're using a CSV agent to um, learn the CFC data we have, and after that, I give the LLM the data description, which is what each column stands for. So as you can see, SQL data stands for the date of the event, actor one country code, actor one type code. I think my teammate has already explained what each of these stand for. And then we pass this data to the LLM and ask it. We give it a new data without the output. So here, as you can see, I've given it a simple empty input without the output, and I've asked it to give me the predicted output value for the last row. And as you can see, once I run it, it gives me the final answer G. So G stands for violent demonstration. So for what it means is for that row of news, it predicted that violent demonstration would occur between the two countries provided. Because of financial constraints, I won't be running this and showing it to you here, since the OpenAI API is charged. Yeah, so this was a collection of all the models we have worked on. In the future, we will be trying to improve the existing models we have, including the KNN and the HMM, and we'll be trying to train it on larger amounts of data. That was a demonstration of the code. Thank you.